Okay, so we're back again, and we're going to be talking about reaction rates. And this time, instead of calculating reaction rates, we're going to learn how to measure reaction rates. So using different types of experiments. Anyways, one way we can measure reaction rate is looking at the change in color. Now, a rate is always going to be a change in something over a change in time, or in other words, a time interval. So you're going to calculate the rate over a very specific portion of time. So in this case, if we have like a reaction that is turning from brown to clear, we can measure the degree of brown it is and how fast does it turn to clear, and we can calculate a reaction rate from that. So we can calculate this by going a change in color over a change in time. Now, if a reaction is exothermic and releasing a lot of heat energy, and therefore making our system much warmer, then we can also calculate a temperature change and use that to calculate the reaction rate. Or if something is endothermic and it's absorbing a lot of energy, then we can find that the system is going to become much cooler, and therefore it's still going to be a temperature change. And if you put that over time, you can then also find a reaction rate. So it's always going to be over time because it's a rate, and you can find a change in temperature over a change in time. Can calculate a reaction rate from that. Now, moving on to the third one, we can also use pressure to calculate a reaction rate. Now, if we're having a few liquids, two liquids, and they're reacting with each other and they're producing a gas, then that gas is going to increase the pressure of the container that it's in. And an increase in pressure over a change in time, well, you can calculate the reaction rate. Or if gases are reacting and forming a liquid, then you'll see a decrease in the pressure. Nonetheless, it's still going to be a change in pressure over change in time. Now, again, delta meaning change in pressure over change in time. Now, another good one is, say if you had a solid and it's reacting with something and it's making a gas, but instead of being in a closed system, the gas is just allowed to go on its own way, right? And you then have this whole reaction happening on a balance, on a scale, and it's being weighed. So since this gas is being released and it's going on its own way out of the beaker, you'll see the mass would be decreasing, and when the mass is decreasing, well, you can calculate a reaction rate, and that reaction rate would be a change in mass. Change in mass over change in time. Okay, this is a very common one to use, and this is the one that we did in our last lesson, where we saw something decreasing, and we took a change in our mass and divided by the change in time to calculate the reaction rate at specific points. Now, another one that we can do is if we had some kind of acid, and our acid was reacting, and our acid was turning into maybe hydrogen gas, or our acid was turning into something maybe neutral, then our pH would be changing. If it was an acid, pH would change from something very low, like maybe a pH of 1 or 2, which is a very acidic pH, and it would start to increase, and therefore you're having a change in pH. And a change in pH over change in time, you can calculate a reaction rate. Okay, so here's 5 different methods that you can use to calculate a reaction rate. Now, reaction rates aren't limited to only being calculated using these 5 different methods. These are just 5 common methods to use to calculate a reaction rate. But there's several different ways you can calculate a reaction rate. You can read and practice a little bit about it in your textbook on page 5, questions 7 to 9 in Hebden. And I'll let you work on that by yourself. Now, moving on, I want to take a look at some different reactions and figure out how can we calculate a reaction rate from these things. So the first one right here, we have CH4, or methane gas, plus oxygen is going to produce CO2 and H2O. Now all these are already balanced for us, and what I want to look at is how can we measure reaction rate? So could we use a change in mass? Well, we could, but it's really quite difficult to calculate and find and measure the mass of something in a gas like this, methane or oxygen, and especially when we're also having gas to gas and it's making some other gases. Now, could we use a change in pressure? Well, not really. It's kind of hard here. Now we have gases, and normally you could use a change in pressure, but what we see is we have 1 gas here plus 2, so we have 3 gases total on this side, and we have 3 gases total on this side, so it'll be difficult to measure a change in pressure. But what we do know is when methane burns and forms this combustion and undergoes this combustion reaction forming CO2 and H2O, what we know is that a lot of heat is released. So what you can do to calculate the reaction rate for this one would be something like a change in temperature over change in time. Okay, and that will equal our reaction rate. So we can use this one to do to kind of measure this. Now, if you had a way to kind of calculate the mass of the water or something like that, you could use change in mass over change in time. Okay, but when it's gas, it's a little bit more difficult. Let's move on to this next one. We have solid lead plus we have HCl in aqueous, so we have hydrochloric acid, so solid lead plus hydrochloric acid making PbCl2 in solution and hydrogen gas. So let's think of a few different ways that we can calculate the reaction rate. So if this was happening on a scale, so imagine we have a scale something like this. Okay, so we have a balance kind of like this, and here's our scale, and it reads some number of what the mass is. Okay, so let's pretend our mass is maybe 10.0 grams, just for fun. Okay, and then now we have this reaction going on here. So we have our beaker that's on this scale, and it's filled with HCl. Okay, now what we do is we put a piece of lead in here, right, that, and what we see the reaction proceeds, and we see, well, hydrogen gas leaving the reaction right here. And after a few minutes, after this reaction proceeds, this 10 grams right here is going to turn into, well, since mass is being lost as hydrogen gas that's escaping the system, this number is going to decrease. So what we can do is we can calculate the reaction rate. The reaction rate can be determined by going change in mass over change in time. Okay? Now, using a different method, what we see here is HCl is an acid, hydrochloric acid. It's in solution, so it is an acid. So when this reaction is proceeding, what we could have is we could have a little sensor in here, and this could be hooked up to a pH meter, and this will give us an electronic readout, an electronic thing, and tell us what the pH is. And well, HCl is going to be used up, and so the pH is going to start off very, very low. Okay, maybe a concentrate pH of maybe 1 or maybe 2, and then the pH is going to start to increase. So we can calculate the rate of the reaction could be the change in pH over change in time. So these are two different ways we can calculate the reaction rate for this one reaction. Okay? Now let's move on to this next one right here. We have nitrogen gas plus hydrogen gas making ammonia gas, NH3. Now what we see here is we have one nitrogen gas and 3 hydrogen gases, and they're making 2 they're making 2 ammonia gases. Now, so we have 4 gases turning into 2 gases. So as this reaction proceeds, using Avogadro's theories about gases, the amount of gas is going to decrease. Okay, so the amount of gas is going to decrease, and therefore the pressure is also going to decrease. Okay, and so what we can do is we can find the reaction rate based on the change in pressure over change in time. Okay, so that's a little way we can do it. Now here's another reaction going down here. We have nitrogen dioxide turning into dinitrogen tetroxide here. Now nitrogen dioxide is usually, well, it is red-brown in color, and dinitrogen tetroxide here is colorless. So what we can use this one, what we can do here is we can calculate the rate of reaction using color change. So the change in color over, again, change in time. Okay. Now we could also use the change in pressure over the change in time for this one too, because we have 1 gas here and 2 gases here. So we're going to see it as this reaction goes forward, we're going to see an increase in pressure. Okay. So we see a whole bunch of different ways, depending on what kind of reaction it is, we can use a different method to calculate the rate of reaction. Okay, let's move on to the next slide. Now I want to talk a little bit about the factors that affect the reaction rate, things that can increase or decrease a reaction rate. So the first one is temperature. Now this one is very, very important. So temperature is essentially just energy. If you increase the amount of temperature or increase the amount of energy, then the rate increases. Now the question is why? Why does that happen? Well, if temperature is increased, then the amount of times that molecules bump into each other and hit each other increases. Temperature is going to increase the amount of kinetic energy that a molecule has. So a molecule is going to be moving around a lot more, and it has a greater chance, a greater probability of hitting another molecule. So there's going to be more bumping and more collisions, and therefore an increased rate of reaction. Also, when you increase the temperature, it increases the energy and increases the force of the collisions that molecules are going to be striking each other. And therefore, you can have, since you have an increased collision strength, you're going to have an increased reaction rate. So that's how temperature affects reaction rates. Now concentration here also increases the rate of reaction. So you increase the concentration, you increase the rate of reaction. Now, the reason that is because concentration means if you increase the concentrations, there's more molecules, and therefore there's more stuff to hit. So there's a higher chance, again, that probability, there's a higher chance of things hitting each other. A higher chance of collisions, more collisions, and therefore, again, your rate is going to increase. Now pressure is an interesting one. Pressure is very much related to concentration. If you increase the pressure, what you're doing is if you increase the pressure, you're taking a volume that is, maybe about, say, this size, and if you increase the pressure, you take all the particles in here. So let's pretend that we have maybe 1, 2, 3, 4, 5, 6, 7, 8, 9 particles in this box, and they're moving around. And we increase the pressure, and we increase it by decreasing the volume. We put it into a smaller box. And when you do that, well, before we have 9 particles, and now we have the same 9 particles. I think that's 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, somewhere around there. But anyways, what we see here is the particles are much, much closer together. And when they're closer together, there's more chance of them hitting each other, and therefore our rate increases. Okay? Now, the next one, the fourth one that we have here, is the nature of the reactants. Some types of molecules and particles are just going to react faster than other types. That's what we mean by nature of the reactant. Some things are just better at reacting than other types of things. And it all depends on the amount and type of bonds that need to be broken. Okay, it depends on their electron configuration, it depends on their electronegativity, it depends on many, many different things. But we can just chalk that all up to the nature of reactants. Some things react better than other things. Now, another one that we have that can increase the reaction rate is a catalyst. Now, a catalyst is very, very unique. It is a chemical, but it is a chemical that will start in the reactants and will also be on the product side. So it will cancel out. So if you have, say, a catalyst, let's pretend we have a catalyst here. Let's make a mock reaction. Catalyst. And we put this with a reactant. Reactant A. Okay, and we're reacting reactant A with reactant B. Okay, and this is going to make C. Okay, so A plus B makes C. But if we add a catalyst here, it'll increase the reaction rate by decreasing the amount of energy A needs to hit B with. Okay, so it decreases the amount of energy that is needed for A and B to strike to form C. But the interesting thing about a catalyst is that it is part of the reaction. However, at the very, very end of the reaction, it is made again. Okay, and so therefore, we don't even, usually in reactions, we don't write it. We just write A plus B makes C. Okay, so it's a little bit interesting. And as here we say, it's not part of the final products. Okay, we don't really write it in these reactions here. So catalyst is present, and when it is, it'll decrease the amount of energy needed for a successful collision. It'll assist in that, and therefore it increases the reaction rate. So here's 5 different ways we can increase, or 5 different things that affect reaction rates. Now another thing that kind of increases reaction rates is surface area. If you increase the surface area, what it means is you increase the surface area, and that means there's more stuff to hit. So let's imagine we have something like again, I am always a big fan of the box. Okay, now here's a box, and let's pretend it has dimensions that are 1 centimeter by 1 centimeter by 1 centimeter. Okay, so 1 centimeter by 1 centimeter by 1 centimeter is 1 centimeter cubed, or in other words, 1 milliliter of volume this box has. Okay, now if we're to do surface area, it'd be 1 centimeter by 1 centimeter, or in other words, 1 centimeter squared. And then we just add that by 1, 2, 3, 4, 5, 6 centimeters squared of surface area. Now what we can do is, if we take this 1 milliliter and we just flatten it out, we just flatten this thing out so it's really thin. Okay, but it's really big like this. So we just like take a little roller and we kind of rolled it out and flattened it all out. Now this is also going to be the same amount of volume as this. However, the surface area has increased greatly. And since the surface area has increased greatly, there is more places for reactants to strike it. More strikes, more collisions mean a greater reaction rate. Okay. Now, the surface area is only going to apply to heterogeneous reactions. Now, what is a heterogeneous reaction? These are things like a solid plus a liquid. So if you increase the surface area of a solid, well, you're going to increase the reaction rate. So this is one. If you maybe a liquid plus a gas. Okay, if the gas can come into contact in a lot of area with the liquid, well, you'll have an increased reaction rate. And solid and gas, and you can even have liquid and liquid if these are unable to mix, so like something like that are what we call immiscible, like a water and an oil. They don't mix. You can clearly see that they don't mix, and therefore it is heterogeneous. Now, homogeneous reaction is something like 2 liquids that do mix, or an aqueous solution mixed with another aqueous solution, or 2 gases. Surface area, if you had a gas plus another gas and they're mixing just fine, increasing the surface area, well, that won't have any kind of effect on this kind of reaction right here. Now, another thing that will affect reaction rates is the phase, or what state something's in. So we have here aqueous, liquids, and it should be gases here too. Liquids and gases and solids. Now, aqueous is the fastest, and solids are the slowest. Now, why are solids so slow at reacting? Well, one reason is that the molecules in a solid, or the particles in a solid, are not moving very fast. Are not moving, and therefore not colliding. Okay, they're not really moving, they're not colliding, and not mixing with other reactants that it needs to be reacting with. Okay, so solids are quite slow. They're not really moving as much as we may have hoped. Now, liquids and gases, they are moving. The molecules are moving much faster, so particles are moving faster. Particles are moving fast. Okay, so particles are moving much faster, and therefore they can mix and collide. So therefore, this symbol means therefore. Therefore, they mix and collide. And reactions can happen much faster than solids. Now, aqueous also has particles that are moving faster, because aqueous and liquids, well, they're essentially the same, except this one is just something that's dissolved in water. So aqueous solution is moving around just as fast and just as much as a liquid solution. So particles are moving just as fast here. So particles are moving also fast. And therefore, they mix and collide. Exactly the same as I wrote there. Now, what makes aqueous have a faster reaction rate than liquids? And the big thing is like when something is in solution, right, there's a lot of positive and negative. Like when something is dissolved in water, water is a polar substance, and it's going to take an ionic compound and really break it apart and create positive ions and negative ions. And those positive ions and negative ions, well, they're going to be positive and negative. And things that are positive and negative are more likely to hit each other. So there's going to be more collisions. There's going to be more collisions here because there's things that are positive, because I'm just going to write this in a different color. There's positive things. There's positive. This is my little mini symbol for positive. Positive, and there's also negative. So there's positive and a negative, and well, positive and negative are more likely to hit each other than two things that are just neutral. They're attracted to each other. So more collisions because positive and negative attractions. Okay, so again, solids are the slowest, particles are not moving and therefore not colliding and not mixing. Liquids are faster, they're going to have a higher reaction rate because particles are moving faster and therefore they do mix and they collide. Now aqueous is the fastest for the same reason. Particles are moving fast and they mix and collide, but also there's more collisions because there's positive and negative attractions. Okay, so the positive and negative are going to be attracting each other and they're more likely to hit each other. Now let's move on to the next slide. And this next one is a inhibitor. Now an inhibitor is interesting. It is a chemical that decreases the reaction rate, so it's kind of like an opposite of a catalyst. Now an inhibitor combines with reactants to prevent them from reacting. So let's pretend we have a reaction like this. I'm going to kind of make something up here. Let's have a reaction like our other one before, and we have something like A plus B, and it makes C. So we have this kind of reaction right here. Now let's pretend we add, and let's add some numbers here just for fun. Okay. So we have maybe 1.0 molar, and this one's also going to be 1.0 molar, and this is C is a larger particle than A and B, because it's just, I guess I can, instead of writing C, I could have wrote AB, but that would also be 1.0 molar if it went to completion and completely reacted. But let's pretend here, so in this one right here, all the same volumes, nothing is being limited, nothing A nor B is in excess. But let's pretend we add something like this little Pac-Man character. Let's add a Pac-Man character. And it's blue. Now, as we see here, the letter A fits perfectly in there, upside down, of course. And this Pac-Man character kind of bites onto the letter A right here with its big teeth. So it bites onto the letter A, and it does not let it react with the letter B to form C. Now, this letter A, let's pretend I add a few particles of this A. So what it does is, this is an inhibitor. This would be an example of an inhibitor. Slight spelling mistake. But this is going to grab a hold of A and not let it react with B. So therefore, A is then going to be limiting. So even though our concentration of A is 1.0 molar, the amount that can react with B, well, some of this A is going to be tied up with the inhibitor. So instead of being 1.0 molar, it's going to be like maybe 1.75 molar. Because some of this is being held by the inhibitor, and in fact 25% of it is being held by the inhibitor, and therefore your reaction rate, there's still some A that's left over that can still react with B and form C, but since the concentration is like it's being less, since the active concentration that can react is less, the reaction rate is decreasing, because the active concentration that can react has decreased, reaction rate has decreased. So inhibitors combine with reactants to prevent them from reacting. They're still there, the reactant is still here, it's still okay, it just is unable to react with B now. And inhibitors are not part of the reactants, and they're not part of the products. Okay, they just hold on to some of the reactants and don't let them react. And that's what they do. We use inhibitors all the time in our body to regulate all different types of biological functions in ourselves. Now, let's take a look at how you can measure the experimental measurement of reaction rates. So right here we have the first question. It says, using the graph, calculate the reaction rate at exactly 30 seconds. So I don't want a time interval between 30 and 45 seconds. I want the reaction rate exactly at 30 seconds, almost kind of like the instantaneous reaction rate at 30 seconds. So how you can do this is you can calculate it by, well, drawing a tangent line. So here's my tangent line. Here is my 30-second mark right here, and here's my 30-second mark right here, and what we see is we draw a tangent line, and it looks like it crosses about 6 grams and maybe about 63 or so here seconds. So we go 6 divided by 63, and that, so in other words, our rise over our run, or our change in mass over our change in time, and we see that 6 over 63, and that gives us a reaction rate of 0.095 grams per second. Now, if we were given a question something like this, saying, using the time interval, find the rate between 45 seconds and 60 seconds. So again, now we're looking not at the instantaneous, but over a specific time interval. So right from here to here. Again, we want to go the change in the mass over the change in time. So the change in the mass from 1.5 over 1 is, the change is a half a gram, and the change in time is 15 seconds. So the rate is going to equal a half a gram over 15 seconds, and that's going to be equal to 0.033 grams per second. Okay, so now we have learned how to measure and what tools we need to measure reaction rates with, and here's a little bit of practical aspects of taking a set of data and then calculating our reaction rates at specific times. Okay. Good luck, and read your textbook in Hebden, and if you have any questions, ask me during class. Okay, bye-bye.